Hello everyone, welcome. My name is Ron Stone. I'm a senior in aerospace engineering. I have a minor in computer science. I also have a minor in Germanic studies. I'm graduating from the University of Michigan, but I'm coming back for a master's in aerospace engineering next year through the SUGS program. And this is my honors Capstone project presentation. It's a pleasure to have you all here. So the title of my project is Development of Visual Educational Software for Undergraduate Aerospace Engineering Structures Courses. So the title is a little bit contrived, but I promise it will be clearer once the presentation gets going. So the project has been developed entirely by me, and my advisor has been Professor John Shaw. Professor Shaw is a professor in aerospace engineering here at the University of Michigan. So let's talk about the problem statement. All undergraduate aerospace engineers must learn about structures. This is critical when designing aerospace components because there's a trade-off between safety margins and weight. Now, this is particularly important for aerospace engineering because it has one of the industries with the lowest safety factors. And that is because aerospace engineers do not want to make aerospace components very sturdy because that involves a lot of mass, which in return makes them weigh a lot and which makes it hard to get things off the ground. So every good aerospace engineer must find a happy medium between safety margins and the weight of the structure that they're designing. At the University of Michigan, 2 courses focus on this area. Aerospace 215, which is Introduction to Solid Mechanics, and Aerospace 315, which is Aerospace Structures, and focuses on thin-walled structures, usually seen in aerospace engineering as, for example, the wing of a plane or the fuselage of an airplane, etc. So as a senior who has taken both of these classes and someone who has talked to a lot of people who also took these classes, I've noticed that the lack of visualization tools hindered the learning experience. So what do I mean by that? Well, first of all, it has been shown multiple times that visualizing a problem, visualizing the content that you're learning, enhances dramatically your comprehension of the subject matter. It keeps you focused on what you're learning, and it helps keeps the audience, which is the students, engaged in the course. So for someone who has not taken these classes with the aid of these tools, they haven't been very available, I decided to take on this project so that I could make sure, or at least attempt to make sure, that other students after me who will be taking these classes for many years to come, hopefully, will be well served in that regard, that they will have this kind of tools at their disposal to enhance their learning. But I did not only choose this project because I wanted to help students, I also chose it because I'm very passionate about education and teaching. That is one of the reasons why I'm coming back from graduate school. And also, I wanted to make good use of my computer science minor so that I could put my skills, into a project that is meaningful in many different ways. So when I talk about visualization problems, what I exactly mean by that? Let me give you a quick illustration. So consider this classic truss problem. This is a problem that is usually taught at undergraduate classes here at the university. And the way students usually go about this when solving the problem is that, well, they're required to find the displacements at each node from 1 to n. In this case, there's only 4 because it's a simple problem, but it could be 100 nodes. It could be, a much bigger truss. And after they find the displacement, they have to calculate the stress at each member. And the member is what connects the nodes, so the segments in the truss. So what students do is that they do all of the math, they do the matrix manipulation, the matrix multiplication, and they end up with a result that looks somewhat what you see here, a table of results. And they usually call it a day and say problem solved, there's nothing else I can learn from this. But I think that there's a fundamental issue here, which is students, they see the results, they get the right answer, but they don't have a physical intuition of what is going on with the truss. They don't understand how the solution affects the system. And it's hard to see. It's just a table of numbers, right? How can you see what exactly is going on in this problem? So what I suggest is to have a software that can solve these problems and give you a better understanding of what is going on through visualization. So my approach, what I suggest is to have a software that gives you a representation such as this, clearly telling you what is going on in the problem, which members are in compression, which members are in tension, which members have no stress in them, the displacements. Like this, students can have a much better understanding of what is going on with the structure. It's very hard to see from this image and from these numbers that, for example, member 2 is in compression, member 4 is in tension, and the others have no stress at all. So this could give students a much better comprehension of what they're solving, of the solution, which is fundamental in my opinion. So let me now give you an example. It will be of a different problem, a beam modeling problem, from the software that I'm developing. And you can see here its prototype. This is the beam solver for the software that I'm writing. If you're curious, you can go back, solve other problems. This is the main page. So let's return to beams. So for example, the curious student might, when they first see the software, they might just want to run this button, which is very tempting, just run, right? But this program is filled with safety checks to make sure that the students are solving the problem that they want to solve. So here, for example, beam parameters are undefined. So the student goes, okay, I would like to define my beam, give it some properties, and they run again, and it says, well, beam not supported. Of course, this is a solid mechanics problem. The beam cannot be floating in the air. So students go, okay, there's an option here for fixing the left end. Let's do that. And there you go. The whole problem and its different parts are displayed right in front of the student. And the idea is that they can prototype, they can experiment with this. If they want to solve a very classic problem, for example, of adding a point force to the end of the beam, they can do that. And a point force is added to the end of the beam, and the solutions are represented so students can have a physical intuition of what is going on. And this could be used in parallel with the classes. So as we solve beam problems on the board, we can also solve them numerically in a computer and see how the structure behaves. And this is supposed to be very modular, so students can change parameters whenever they want. And see, just increase the length of the beam by 2, and the problem is solved automatically again for them. And this includes all sorts of things. You can add pin joints as well at the end, if you'd like, as you can see here. So this would be a great tool for students to use and have a better understanding of the problems that they are solving. So this project is very open-ended in many ways because, well, first of all, the concepts are not only relevant for aerospace engineering. These are taught in material science, mechanical engineering, and many other subjects. Solid mechanics is taught across multiple engineering disciplines, yes. It's not only restricted to the University of Michigan, so my idea of this project was to make it as educational and free to open to everybody as possible. And the software will keep being developed over the years. So what you've seen is a prototype that I'm writing, and it's done to the extent that you can give it to students, and they could use the software already. But of course, you could add as many structures problems as you want, and you could keep improving on the interface. So this project, I will personally be working on it for at least 1 more year during my graduate studies. And I hope that I could find also other students that would join me on this challenge to make the life of students easier when it comes to understanding structures problems. So if you're interested, you can reach out to me or Professor Shaw, and we can have you join our team and work on the software. So this is essentially my project. Thank you very much. I would like to acknowledge Professor John Shaw, who oversaw its development, the project's development, and has always made himself available for advising. Special thanks to Professor Vera, who provided me with the educational content for this presentation, the trust problem I mentioned, and a special thanks to the honor staff for all of the support they've given me throughout the years. Thank you very much.